this is a special occasion on the series of our seminar for mathematical physics, because this is very likely the very last seminar of the semester, and the privilege to close this seminar tour to the mathematical physics has been given to nobody else than Vincenzo Marotta, and he's going to deliver something what we don't know yet, but the title is Relations, Divergences, and
Dirac Structures.
Dirac Structures could be. So, thanks for volunteering, and of course, yes.
Sure, thanks. Okay. So this talk is basically going to be about my ongoing research projects, which are all at the very early stage. So I'm basically going to take this as a huge big therapy session, which I'm going to talk about my problems, and hopefully I'm going to receive some. In a way, why do I have motivations to study, for instance, like divergence operators on topological properties? Well, that's because, again, some people such as Mario Garcia Fernandez, Philippe Balak, Paul Chevera, and these people basically studied this in the context of Poisson-Lee duality, and they managed to formulate, some of them, a notion of Poisson-Lee duality for generalized Ricci flows. Generalized Ricci flows are actually objects that really heavily depend on the definition of divergence operators on Courant algebroids and well, of generalized matrix as well. But I'm going to tell you this in due course. And they provide a way of formalizing Poisson-Lee duality in some sense. Of course, this notion I would like to interpret whatever is in there and a bit beyond in terms of relations of Courant algebroids, in particular of generalized isometries. And this is based on my previous work. So in the previous seminar I gave you here, because we found an alternative way of obtaining a generalized isometry between generalized metrics that wasn't the one previously involved in Poisson-Lee duality. So at least in this first part of the seminar, I'd like to talk about divergences and state, what are the open problems for us in terms of generalized Ricci flows. In the next part of the seminar, if I have enough time, I'll try to discuss how Dirac structures might be, what might be a sensible notion of relation of Courant algebroids between Dirac structures, and how you could possibly use it to define relations between generalized complex structures, at least at the very naive, from that very naive point of view. So in order to actually kind of explain what I meant by my hand waving so far, I would just like to introduce few notions. Again, as you probably already know, a Courant algebroid for me is a vector bundle over a smooth manifold M endowed with a symmetric bilinear pairing, non-degenerate as well, a bracket operation that I often will denote like this, which satisfies, which we're going to see, satisfies some compatibility conditions with the pairing, and draw a map that goes from E to En, which is a vector bundle morphism covering the identity, and it's a bracket morphism between this bracket that I just told you about, the defined sections of E, and the standard Lie bracket on the sections of the tangent bundle. What are the conditions that this structure has to satisfy in order to be Courant algebroid? Well, one is the Jacobi identity for the bracket. I'm not going to write explicitly. The bracket is not skew symmetric, so it has to be urgent for the Jacobi identity. Number two is the compatibility condition between the bracket and the pairing. In a certain sense, the bracket has to preserve the pairing, which again might be written in a way. So the iterative of rho or E1 of the pairing between E3 actually equals E1, E2, E3 plus E1, E3, which basically what I just said. And three, the symmetric part of this bracket is controlled. So how do I want to put it? Somehow, the symmetric part of this bracket is controlled. Okay, I don't want to dive too much in the details because I'm not going to use this relation too much. But the important thing is that actually, if you mix up these two things and the Jacobi identity, you will get that this bracket satisfies a Leibniz rule, an anchored Leibniz rule, so an Leibniz revolving rock. And this is what you all know. The standard example again is the tangent bundle with the sum with the cotangent bundle over a smooth manifold M. And grand algebraics that fit into the short exact sequence are called, in this short exact sequence, are called exact. Okay. And they're all isomorphic to the standard grand algebraic and classified by a three-form H, which is closed and is actually called the Schroeder class when you take it in cohomology. Okay, this was a very short summary. It's not meant to be comprehensive, but we don't have much time to go well into this stuff. So what is the thing I really care about is actually how one can define relations. So an extension of standard maps between grand algebraics, which have been discussed, like, by not so many people, but yeah, definitely a lot. I'm a big fanboy, so and so what do I mean by a relation? Is simply a relation supported over submanifold C is going to be given by the coordination. So let me take R to be a let me define first a couple of things. Let's take just two grand algebraics E1 and E2. Let me define you can easily see that this product, I love this bar, meaning something that I'm going to do in a second. This product is going to be endowed with a grand algebraic structure as well, which is the obvious one that you can take. So on each, basically the one coming from each grand algebraic on each side. And this bar means that the product here is going to be defined in such a way, which is basically the pullback of the first one, the first product. I'm gonna omit the pullback notation minus the one in the second, minus the product in the second. And then the bracket is just gonna be given by the bracket, just the pair of the bracket on the first grand algebraic and the bracket on the second one, the anchor on the first one paired with the bracket on the second one, and so on. So what do I mean by the relation between E1 and E2 supported over a submanifold C is actually where C is a submanifold, an embedded submanifold of M1 times M2 is just a vector subbundle restricted to C, which is isotropic with respect to this guy. It has to be involuted with respect to the bracket that is just given by, okay, let me write it. And it has to satisfy a compatibility condition with the anchor. Let me put it that way, where the anchor, again, is just what I told you. Just this. And it's that rho R, was it rho R? Yes. Well, rho R is going to be into C, and I think rho of R curve has to be in, has to land in BC. Such it was that. It was definitely that. I definitely need that. So this is basically an extension of a map between E1 and E2. Actually, if you take, for instance, E1 and E2 to be isomorphic, you're going to see that R is just going to be the graph of the isomorphism supported on the map that means diffeomorphism, the graph of this diffeomorphism covering this isomorphism. And one special kind of relation is the one in which C is actually the graph of, say, phi, where phi is a smooth map from 1 and 2. And these are usually called classical grand algebraic modes. Okay, so if C is the graph of the smooth function between two manifolds, well, R is going to be what we call a classical grand algebraic mode. Okay, why do I need all this thing? Well, it's just because in my understanding of T duality, these guys play like a big, huge role as generalized isometries. I try to introduce this notion in a little while without going into much detail, as I'm not doing right now. But what do I mean by generalized isometry? So between what? Between generalized metrics, which are simply given by, again, V plus. A generalized metric is simply going to be given by a vector subbundle V plus, which is maximally positive definite with respect to the inner product here. So in this, for instance, if E is exact, so it has to have even rank, the rank of V plus is going to be half the rank of E. This guy does not have to be positive, for instance. And the standard example when you have that TM, oh well, let's say in this case we can take V as the graph, for instance, of a Riemannian metric G on your base manifold. This is like B. Basically, it all covers all the possibilities you have. What happens when we want to define a relation between generalized metrics? Well, you need to do something more. You need to impose some conditions. So let's assume you have two generalized metrics, say V1 plus V1, V2 plus, not plus V2. How do I define a generalized? Well, an easy way to see it in terms of subbundles is the following. So let us take, let me define V plus to be just the product of V1 plus and V2 plus. Okay. And let me take the minus to be V1 minus product V2 minus, where V1 minus is just the orthogonal complement of V1 plus. So it's going to be negative definite with respect to the inner product. Let me then consider these two objects, and then I'm going to say that there exists, say, the V1 plus. There's a generalized isometry R between V1 plus and V2 plus if we can split any point P on if we can split R in this way. So this is one way to formulate this condition. The other obvious way would be, which is also the first one I think given by Jan, is the one in which you consider tau to be the automorphism squaring to the identity of E1 and E2. Consider the product on E2, on their product on the quantity product given by E1 times E2, and then you just consider the, I'm going to call this guy tau 1 and tau 2. Even by tau, if you actually have that R is preserved by tau, then it works. And you actually, these two notions are good. I'm not going to tell you why, but they are. Actually, I did it in my previous talk. So, and it should be true. Why do I care about this? Because in our formulation of T1, which is kind of, should be kind of close to a sort of physical interpretation of T-duality in common sense, that is not possibly T-duality, you are able to construct a diagram which is not commutative that goes this way, and I'm going to tell you the objects involved in this diagram in the following part of the talk. So you have these two related current algebroids by a by an isomorphism phi. You take the quotient of these two current algebroids, so you reduce them by a foliation. I'm going to tell you what it means in a second. So these are going to be the relations defining the reduction of these current algebroids. You obtain two reduced current algebroids, and these two guys are actually related by a relation R. Under suitable circumstances, if you endow E1 red, the reduced E1 current algebroid with a generalized metric V1, let me call it V1 red, and this generalized isometry satisfies some conditions, some invariance conditions with respect to a foliation on this manifold on this manifold endowed by this other foliation, then you're sure that there exists only one, a unique generalized metric on this one that is induced by basically pulling it back and carrying it forward, such that R is a generalized isometry. And this is what I mean by T-duality. So by T-duality, I mean somehow the only chance in which I can construct this diagram and make sure that this guy, this relation is actually a generalized isometry. Our main result actually in our previous paper and in my previous talk is actually a result of the existence and uniqueness of this generalized isometry, of this generalized metric, sorry, once given this one. Okay. I guess it's not, because I didn't tell you a lot of things. But I'll try to make this diagram clear as far as I go going on this talk. In particular, I will try to tell you a little bit more about these maps that are given by the reduction of chronological by these relations given by the reduction of chronological. So why did I want to tell you all of this? Because the main point of discussing divergence operators for chronological is actually when they are compatible with generalized metrics. Because in that case, one can define a notion of generalized Ricci tensor that, for instance, for exact chronological, so in this case, coincides with the standard notion of Ricci flow, generalized Ricci flows, which in the case of exact chronological coincide with the standard notion of Ricci flows for some connection, for some suitable connection. So the idea would be to try to find a way to introduce a relation. I mean, it's actually the main goal would be to show that whenever you have a divergence here, and you can construct a generalized Ricci flow here, this guy, this relation here, which is generalized isometry, is also telling you that you have a T-dual generalized Ricci flow. These objects are usually interpreted, I think, in terms of equations of motion of some type of supergravity. I am not an expert on that, but I just want to stick to this diagram and basically start trying to construct some generalized Ricci, or some, at least at this moment, just some divergences that can be carried to this side. Because if that's possible, there's a good chance that also generalized Ricci flows are going to be carried by this diagram to the other side. Okay, so what is a divergence operator then? Let me define it simply as stay here. So your definition. So let E over M be a chronological. And let me tell you this divergence operator. In this case, I'm just going to consider a divergence operator to be a map that goes from sections of smooth functions on N, such that it satisfies the following Leibniz rule, which is so it's not linear. It's not simply linear. That's pretty much what I'm saying. And it's actually, and it is not in a controlled way, which is almost like having a Leibniz rule, as close as possible, where E is clearly any section E and F a smooth function. Okay, is also referring to smooth function. So the point would be, how do I define a sensible notion of related divergences? Well, this is going to be complicated, mostly because there is no, well, it will carry some problems. I will just tell you the definition of related divergences, and then we will discuss some problems. So again, definition. Let me assume that I have a grand algebraic relation here, supported on C. And let me assume that I have two divergence operators. Okay. So when are they related? Well, the definition I'm going to try to give is simply that if one is related to if for any E1 and E2 sections of E1 times E2 are. By this notion, by this notation, I simply mean that whenever I take the restriction of E1 and E2 to C, these are going to be sections of R. Okay? And this is also, I would have told you in a different way, that E1 and E2 as sections of E1 and E2 separately are related sections. Okay? So what do I mean by this is that for any element in here, we have that divergence 1 of E1 is a C-related function to divergence 2 of E2. What do I mean by C-related function? Let me tell you like that. Let's say that I have, again, two manifolds M1 and M2, and I take two functions, F1 in M1 and F2 in M2. Yeah, this means nothing. Smooth function on M1, smooth function on M2. What I mean for them to be C-related, so if F1 is C-related by F2, if I have a submanifold C of M1 times M2, such that basically, let me take the pullback of F1 to M1 times M2. This is just the first projection of this two manifolds to the first product. Restricted to C, this is actually equal to the projection to start. So the pullback of F2, again, to the product restricted to C. So if this happens, these functions are said to be C related. Okay, and in this sense, I mean that the divergences are related. So for any R-related sections of E1 times M2, these divergences are related functions. Okay. Okay. So for instance, in the case of classical current algebraic morphisms, this simply means that divergence 1 of E1 always has to be the pullback by the smooth function phi of divergence 2 of E2. Okay? According to this definition, which is sensible. Problem is that I'm hiding some problems here under the rug, which are given by the fact that some divergences might take some specific form. Which is given by the fact that, well, they might be defined in terms of current algebraic conditions. And this might be a problem because, let's say, if you have a divergence, okay, I'm just going to tell you that the divergence lambda is a current algebraic connection that is just an object, a map that goes from, say, the current algebraic E to E that basically satisfies a Leibniz rule in the second entry. It preserves the inner product and is simply linear in the first entry. And that's what we need to know as a current algebraic connection. Well, you can define, for instance, a divergence operator by taking like to any section E of an algebraic as the trace of number. Okay. Well, there is a notion due to Young of unrelated current algebraic connections, which is actually what you would expect. So if I take two current algebraic connections, number 1 and number 2, on E1 and E2 respectively, I define the product on E1 times E2. Again, what I'm going to claim is that number 1 and number 2 are related if you take any, if this happens, for any E, any prime sections, again, of E1 times E2, that take values in R. So basically, when you restrict everything to C, this again needs to be an element in a section of 1, which is a very sensible notion. If you actually try to infer that such two, okay, then let's take two divergences defined by number 1 and number 2. Are they going to be related in this sense if their two algebraic connections are related? No. Well, or at least we cannot prove it. And the main obstruction, as I think Young points out in this paper, is but the trace operator is this. I mean, this trace closer So at this point, this is one of the first problems that we have. We might sidestep it because we do not necessarily need our divergence to be defined in such a way. As shown in Shimada, for instance, the generalized redshift level might be a quantity that is completely independent on the choice of chronological condition. So I will actually going to sidestep this problem completely and just consider the generalized redshift level is going to be used by a divergence and the generalized method in some sense, but I'll try to bring it.
Just trying to think of more examples of how to confirm divergences.
Yes.
Let's say we have volume form M.
Yes.
We have a standard divergence subvector of that.
Yes.
And let's say we pick any Coulomb-Cauchy vector.
Yeah.
Can we always split it up some?
Yeah. That's the precisely difference. You just use the anchor pretty much. Because you can take the derivative on the anchored vector field, anchored section, and that's basically just to the chronological rate.
And in the simplest case, M is a point, so we have like that's the algebra.
Yeah.
So in this case, divergence seems to be like any unique.
Indeed, I think so. Because the inverse will be just
Yeah, but usually it's very interesting.
yeah, exactly. It works perfectly fine. I think there's also good points why in the end it works when you want to go back from generalized Ritchie flows to the standard. So you always have a way to, for instance, when you want to do it for connections, you always have a way of inferring algebraic connections from connections on your native bundle of any. It is a similar approach, but still, yes. In any case, actually, this was the first example I was going to mention with volume forms. And maybe I should do it because despite the fact that this definition I just gave you doesn't work for this kind of connection, well, at least doesn't behave in the way you'd like it to be in the case of divergences defined by chronological connections. It does work well, for instance, for divergences defined by volume forms. For instance, erase. What do I mean by this? Let me introduce a notion of a related densities, which is going to be not too much arbitrary. So let's say that this is the wrong choice, isn't it? Let's say that M1 and 2 are zero manifolds, so it makes lots of manifold in the product. I'm not going to assume it's closed in the undefined. I'm going to assume that M1 and M1 are not like densities mu1 and mu2. So we can say that mu1 is related to mu2. Can you see anything over on this thing? Is it photo? Probably not. Right. So I'm going to say that mu1 is related to mu2. If the loading happens. So take the pullback again by the first program of mu1 and restrict it to frames on C. This needs to be equal to the pullback of mu2 to the product of mu1 and mu2 and restrict it to frames on C. By the process here, restricting the frames on this seems to be a sensible notion. For instance, what happens if you have that C is the graph of a smooth map phi that goes from 1 to mu2? Since, well, with mu1, mu2 densities, this thing just tells you that mu1 needs to be the pullback of mu2 as a density. Okay? So this is a short example of the purpose. So what happens in terms of well, divergence is induced by volume forms in this case. I'm going to take, say, lower vanishing densities. Well, the idea is actually quite simple, and I can state it in a very simple fashion. I'm going to make it here because I don't have enough space. It's
again, let me define a density. Suppose P1 and E2 are both relative roads over, and 1 and 2 are equating numbers. So E1 and E2 are weight forms. Let me define divergence E, where E goes from either 1 to 2 as PI, you have which one is variable in rho E to the right of the I of E, okay, where I can be the other one. Then, mu 1 is C related to mu 2. Then, let me just leave mu 1. Let's make it precise. Then we actually have, as a lemma, we can prove it. But divergence of mu 1 is actually unrelated. I'm assuming that our line is only to sorry, is actually unrelated from the pros with the relation support on C. Then dPi is unrelated to the dPi is unrelated to the this calculation. I mean, it's rather it's not just there's a few technical steps. Okay, I'm not going to prove it because but there is not. So this is at least the definition I gave you is consistent with this simple case. Why do we care about this? Well, because in a sense, we can actually show some nice properties of divergences and also algorithm. For instance, we can always say that if the difference of two divergences, say we call it the break A, this is always going to be given by, so we can take this form for some section in your quantitative break. Okay. In particular, if your quantitative break is mixed divergence such as this one, then you're always going to consider this difference. For instance, suppose that your quantitative breaks omits a generalized metric. Well, you can always rewrite the generalized metric in terms of a remaining metric, pretty much. There's always such a choice. So you can always take the fifth layer is mu to be the starting form used by the metric. So it's always going to characterize this difference, it's always going to characterize somehow our divergence. Of course, this depends on the choice of mean. But if we have such choices, and suppose then that we're in such a position in which we have mu1 and mu2 to be unrelated. So mu1 and mu2 to be C-related volume forms. Then, if we actually have that, this is the condition that in the timing two sections characterizing divergence on both sides. So now in this condition is only the assumption of this element. Then I can show you that we have that D1 is unrelated to D2. So I'm just assuming that mu1 and mu2 are zero. This is it. And this is true if and only if E1, E2, where E1, E2 are
If this section is defined by this difference are sections of E1, E2 are perfect. Okay, so this is true. Well then, and clearly, if R is the Dirac structure, well, this actually becomes this actually tells you that E1, E2 have to be unrelated sections. This doesn't happen in general. This is the most important. But it does happen when R is a related section. Why do I care about this information? Because this guy, this generalized isometry, is always going to be a Dirac structure in the product. So this actually is important when you want to transfer things on the other side and then prove that this guy is a relation between these two divergences. Okay, so this is basically one of the important parts that we need in order to construct well-defined divergences. And one more important bit of information about, general stuff about divergences is that we can use this IE, this I section of our current algebroid to define a iteration operator, which is simply going to be given by E, and I'm just going to take it as basically the Dorfman bracket. So this the current algebraic bracket of E with, let's say, with this guy that I can call it, okay, say big. You know that it's the one introduced by the divergence. Why do I care about this thing? Well, because long story short, if we're in these conditions, so if div1 and div2 are unrelated, and we are in this setting here, then we have that add E div1 is again unrelated to what E div2. In particular, this derivation operator does not depend on the choice of volume. This can be shown, has been shown, I think, by Garcia Fernandez, maybe also Chever and Balak. I think Chever and Balak, right? Yeah. And so the point is that then you also have a well-defined notion of this derivation operator. Why do I care about this derivation operator? Because this is going to be the means I'm going to use to define compatibility of divergences with generalized metrics. What do I mean? Here in our looks like it's ready. So what do I mean that a divergence operator? Again, preamble is always that I have a current algebroid, I can define a divergence operator, and I take a generalized metric V plus on my current algebroid, and I have this defined on me. So what does it mean that the divergence operator is compatible with the generalized metric V plus? Well, is that the derivation operator add E div does such a thing. So let's say that add E div for any V plus is again a section of V plus. For any V plus section of V plus. So basically we're saying that in some sense the divergence preserves the generalized metric. Okay, and this is actually important for us because this is a well-defined notion with respect to generalized isometries that exist somewhere on this board. Here. This is a well-defined notion with respect to generalized isometry. So what am I saying is that I'll tell you in a second because I need to make more a few statements a little bit more precise. So I told you about this thing, and now I can just claim. No, actually, I think I can just claim what I meant, which is simply that. Well, I can simply claim yes that that if you have unrelated divergence operators, well, and R is a generalized isometry between the two generalized metrics, then the divergence are also get the divergence. Sorry, I need to state it properly. So let's say that I have divergence 1 to be unrelated to divergence, and say that divergence 1 is compatible with a generalized metric V1. Okay, only one. And then say that R is a generalized isometry between V1 and V2. Then we have that also at div at E2 at E2 we basically have, but also is then also the E2 is compatible with the, which is which is actually what you would like to what you would expect from say related divergence operators, how they should behave. Also, we have on a side note, if this splitting of R is globally true, not only pointwise true, then the operator defined on the E1 times E2 by taking the adjoint by taking these derivation operators by E1 and E2 on the product, then then that operator preserves this splitting. Okay. So all the notions that I'm giving, why am I telling you this? Because all the notions that I'm giving you seem to be consistent. So either they're trivial or they're so in this case, this notion seems to be consistent with what we know, and the notion of relation of divergence that I gave. Why do I care about this? Because I also want to, well, one main point in studying T-duality is understanding how things are inherited when you take quotients of Ramanujan products or pull back, depending on which side you are. If you're Poisson Lie or this side. In any case, the side shows one important notion that is also being shown in Chevera and Balak, at least for equivariant divergences, is that they're well behaved under that equivariant divergences are well behaved under quotients. So they give you a divergence on the quotient of the reduced chronological. You can do it also in this more general sense of reduction by a foliation of your chronological. You just need a notion of invariance of your divergence with respect to the foliation, whatever is going to be this foliation. So what do I mean by this? Let me take a subbundle of E, which is isotropic, involutive. So by foliation, it means exactly this. If K is involutive, then growth of K is going to be a distribution on the tangent bundle, and the foliation I'm thinking when I think of that reduction is the one integrating this distribution. Okay, and it's going to be a regular one by assumption, at least in the case of example. Then, if I have this div, I'm going to say that div is K invariant if the lead derivative of rho along any section of K of div E actually equals to the divergence of the bracket of E with K or KP, and div of K must be 0. Okay, this is for any E section of E and for any K section of my subbundle. This definition has a slight difference compared to the one that was given in Chevera and Bach, and it's basically not in this part. This actually can stay the same, but it's clear because for G equivariant divergences, you're always going to use them, in particular when you want to reduce them, on G equivariant sections of your chronological codes. Sorry, or G invariant sections of your chronological code, which means this bracket's always going to be 0 there, and this allows you for more freedom here. Actually, they take here to be this divergence of the section of K to be minus the trace of the corresponding element in the Lie algebra, of the bracket of the corresponding element in the Lie algebra of the G action in your chronological code. I cannot do that here because this reduction here by any foliation can be given by can be defined in terms of not only in terms of G invariant sections, or in this case K invariant sections, so sections such that this bracket here is 0, but also in terms of sections that are called basic, that are actually of this type. So E is basic if so E is a section of K verb is basic if is again the section of K. So it doesn't have to be 0. Okay, this is for everything. So a basic section is not invariant with respect to K. So it's not necessarily, I mean, so as you could guess, G invariant section when K is just the image of your Lie algebra action on your algebraic, well, they're just the ones in which this relation matches. In general, this is, I mean, you can also take this freedom that you have when you want to deal with the reductions of divergences, you pay it here. Since this say a basic section is basically bigger than the one, as less constrained with respect to the one compared to the one of G invariant sections, then you have to take this relation to be a little bit more constrained. So what do I mean by that? I actually mean that if you can do that reduction, and I didn't tell you how you do it, but believe me, basic sections are very important. Well, if you can do that reduction, and if you have a actually, you don't have to be able to do that reduction, but you have the notion of of basic section, then you have that if big is K invariant, then, and you also have that you have a mu that is invariant with respect to your foliation, then E div. So the section of E that characterizes your divergence is actually a basic section. Okay, so this is actually the most important result concerning invariant divergences, K invariant divergences, because this is basically telling you that whenever you have a divergence that is K invariant and you're able to do that reduction procedure, then it descends to the quotient. So you actually inherit a divergence on the quotient. And the divergence you inherit is basically going to be characterized by a section of the reduced current algebraic that is given as follows. So let me define this natural map, a curve that goes to E red 1, that is basically given by taking the quotient of K curve by K, and then the quotient of this vector bundled by the foliation. Then the reduced divergence is going to be characterized by this vector field that is nothing but, by this section that is nothing but this. So the natural map applied to it. Okay, so everything looks consistent as well in here, and it is also in terms of mu, in the sense that if you have a divergence defined by volume form, and your volume form is leaf invariant, and you can take actually that the orthogonal part of your mu is, say, the pullback of something from the base. You're basically saying that this big mu operator, if it's K invariant, also descends to the quotient. Okay, so it is consistent also with this notion somehow. Okay. Why is this important? Well, because actually, after doing this reduction procedure, I'm just going to tell you in words. Well, I just mentioned, I didn't tell you why, the reduction procedure is actually can be characterized by a relation of current algebraics. Well, if you do all of this, you're going to find out, obviously, that if you take this divergence to be K invariant and you take the one that you inherit on the reduced current algebraics, well, then they're going to be related by the reduction relation, as you would expect they would be. And same thing happens by definition for the defining section. So it did. Why is this important again? Because if you can obtain your generalized if you can basically get your generalized metric V1 as a reduction of some object on E1, let's say another generalized metric that is compatible with the divergence up top, well, then this compatibility condition of the generalized metric up top and the one on the bottom are preserved. The only thing, because of all of this, the only thing I'm not telling you is that the generalized metric up top on E1, then not on E1 reduced, for me is not strictly speaking generalized metric, but it has an element of non-degeneracy, because in this construction, QK1 has to be as well some form of generalized S. I'm not telling you what kind of objects I'm dealing with, but believe me that in some sense it's for a standard generalized metric, actually QK1, as Jan showed, cannot be a generalized isometry in the case of an isotropic reduction. So we need to deal with slightly different objects. But what I told you works as well. And you can actually preserve this relation. So why is this important? Well, because now I can actually go back to my idea of T-duality and tell you, for instance, take phi to be the identity. Let me take a divergence here with this that is compatible with a generalized metric here. Then, if it is also compatible, if this divergence is K1 invariant and K2 invariant, then I have two divergences that descend from the same one that are also going to be compatible with the two T-dual generalized metrics, which is the whole idea of T-duality that we're talking about. And this leaves us hope, because these are literally the main two ingredients to define generalized Ricci flows on both sides. And this is why they should be T-dual. Main problem, we didn't show it yet for generalized Ricci flows, which is going to be probably the next. Another problem is when you want to consider things that are not necessarily Poissonly-like. So phi doesn't need to be the identity. What is a transformation, a morphism of a divergence? This is a concept that is not super obvious to me. We have some indications, for instance, in the case of B transformations. By B transformations, I simply mean on Tm direct sum T star n, that if you take x plus alpha transformed by B, where B is any 2 for 1n, this is going to be given by x plus ix b plus alpha. Well, one fun fact is that you can define a B transformation of divergence basically by precomposing it. This is going to be a divergence as well. Very obviously, because well, in the end, this guy is simply the linear. So that's the bottom line. And one fun fact is that the section defining div of EB, let me say that EB is the section of Tn by x on this trend defined by the difference of div with some divergence induced by invariant form. Well, this guy is going to be B transformed as well. So the section defining div composed with EP is going to be the minus B transformation of EB. Actually, maybe what is. And also, like, for instance, divergences constructed in this way are invariant with respect to the B transformations. Another fact. We don't know yet how they work. So another open problem, we don't know yet how they work for any, say, isomorphism of chronological weights. And this is something we need to find out. We just have a hint in this case. So I guess for this section, I'm done, and I'm maybe done for the seminar. So we'll probably not talk about.
It's up to you, but
No. I think we're good.
Okay.
No information about Dirac structures. I'd like to end it here with an open problem, but also with the fact that we have promising results in that regard, and the regard of actually obtaining a good notion of T2 generalized Ricci flows in this sense.
Okay,
So, thank
cool.
you.
Thank you very much. Thank you, and it's coming a short time for your questions.
Short question. So in case of generalized metric,
Mhm.
if you just start from the left side
Mhm.
with your T-dual
Yeah.
picture, you can start with B1 and construct B2. You
Yeah.
just pull it upstairs.
Yes,
Yeah.
exactly. Yes.
And can you do the same thing with divergences also?
Yes, at least, well, one of the main points is actually, where is it? This result. That that this is actually, when you want to have a divergence as a scale invariant up top, this is it has to be basic. And the idea is actually that, yeah, then again, basic sections are actually isomorphic to sections of the reduced D1. And that's the main point. So whenever you want to pull it back, you're basically pulling it back by the obvious result. And so basically the obvious pullback by QK. And so you actually get a divergence. What you cannot really get is like the volume form up top. But this also ties in with another problem, which is up top there, I'm dealing with transverse generalized isometries, which in the easiest case, you can think of them as defined by the graph of a degenerate metric. I don't have any sensible notion of volume form associated with the general metric. So how do I do that? One definition might be that in the case of the reduced current algebroids, you might just pull back the volume form from below. It's going to be compatible with the transverse generalized metric up top in some sense, because the transverse generalized metric is going to be given basically by the pullback of the metric on E1 red, and then this might solve the problem in a certain sense. But there is no obvious notion, at least of this thing. But in any case, the important thing for invariance conditions is that you're able to get this guy. And if you're able to get this guy, you can do the whole process.
So the usual statement depends when important to pick up a volume form and consider the divergence operator when this data induces the DV algebra structure around algebra of n. So I was wondering if something like this happens here. Now we may have many different divergences, like we have affine space of divergences. So do we get any structure or something? I guess the analog of the round algebra here is the exterior algebra on the linear dual of E. Right, so maybe it might not form an exact actual complex like this, right? So when it forms an actual complex like you
I actually don't know. I'm sorry about that, but I don't know. I think there was some trying to introduce some notion of cohomology for algebras in the bracket. I don't know how it works, and I don't know if this actually has an element or not in that interest. I think it.
But also, so what we call a generalized metric. So
Yes.
those, so the ordinary Riemann metric induces. So it produces an example of this thing.
Yeah.
Awesome. So how can one make sense of the deformation of it? For example, is there a way to define like generalized KV?
Not in the usual sense, I would say. The thing that gets closer to it is when you want to take invariance with respect to a subbundle by the current bracket. So by the bracket, this bracket here. I am not aware of any notion in those regard. But I guess this might be because in the end, to be fair, this is like a very specific example. It doesn't have to work this way all the time because here I'm taking basically E to be exact. This notion is not related to the fact that it needs to be exact. So at least for exact random choice, maybe there is a way of inducing Killing vector, generalized Killing vector fields in that sense. But in a general case, for any, I sincerely don't know.
Any other question? Doesn't seem to be the case, so please thank the speaker again. Thanks for being faithful. And I brought to offline audience one present. So even before you leave, please take it as my gift to you to not be only faithful but also full. It's maybe. And thanks also people from online audience for their patience. Because as I heard from some of you, some technical problems with the sound appeared. So thanks again to you and Merry Christmas. So,
Bye.
right. Thank you. Thank you very much.